Okay, so Fourier series example. First, a Fourier series, we want a periodic function. So we will, for example, say here is a function. Let me ask you if I'll get a Fourier series for this function is 0, 0, 0, and suddenly bumps up like that, and just like that, and comes down. It's kind of, it's a pulse. Say this is x equal to 0, and maybe this is at some point A, at some point B, and maybe if I say fx, and let's see, this is some capital A. Well, how do I get a Fourier series of this? The answer is, it's not periodic function, so you can't get a Fourier series. Not periodic means can't get a Fourier series. Okay, so let's take another example where we will have some type of periodic function. So this is a f. So let's see, f L of x, we want periodic function. So I have the same kind of stuff. So the A here goes up to say A here, comes back to at B, and this is 0, and this is L, and if I go L plus A, this is L plus A, it goes up again to same, and then comes down. So this is L plus B, and so this is, it looks like this, it repeats, and you can see this repeats this pattern, and this is 2L, and so it's repeating that. As a matter of fact, you could take any L here, so this is the period, and we can say by saying just dot here that it repeats on this side and repeats on this side. Of course, you could take some other period, maybe from here all the way here. That will also be a repeating period. It's also another L. So any one of these will work. When something is periodic, it's periodic regardless of what your starting place is. So suppose I wanted to work out Fourier series of this. We already have a period, and we have the function. So we need, we know what we need. We need sines and cosines of this period. And so let's write this down. I have fx in one period. It's a 0 between 0 and x and a, and it's a between a, x and b, and 0 from b, x to L. So this is over one period. So this is over one period. That's what I need, and then I don't need anything outside of this because we already know it's all periodic and it repeats. Okay, expansion of this function will look like this: a0 over 2 plus summation over all n's from 1 to etc. an, and cosine. So we have we need periods and which are fractions of the original period, and that leads to 2 pi nx over L here, and bn sine 2 pi nx over L here. Okay. And this is also n, 1, 2, 3, etc. Well, we already know the rules for this. A0 is basically 2 over L flx 0 to L dx. And we have the function which is piecewise, so this will break up into piecewise 0 to A and A to B and B to L. So this is going to break up like that, and this will give me 0, and this will be 0, and this will be simply A, B times A. So 2 over L times A, B minus A. So we got A0 is that. How about some M, which would be 2 over L, 0 to L, flx, and then this cosine at 2 pi nx over L dx. Alright, so we already noticed that, I don't need to worry about that, just A to B, and there I just get a constant and get a cosine 2 pi nx over L. So this is just an integral cosine integral will give me sine, so 2a over L times L over 2 pi n sine 2 pi nx over L, and this is A to B. And you can see where it's going. It's going to L is cancelling out, and that's giving me, and this 2 is cancelling out. It's going to be A over pi n, and this is a very common feature you can see in constant functions, where n will come down. It's going to sine 2 pi nb over L minus sine 2 pi na over L. Now we can get rule for Bm will be very similar. It's going to be 2 over L A to B and sine 2 pi nx over L dx. So when I integrate sine, I pick up a sine, so minus 2a over L over 2 pi n. It's going to be cosine 2 pi nx over L A to B. And again L cancels out, 2 cancels out, and this is minus A over pi n and cosine 2 pi nb over L, minus cosine 2 pi na over L. Therefore, we have rules for A0, AM, and AN, and I can plug in for any one of these and as many terms as I like. So if I want to A1, I'll get a value. Suppose if I want A1, B1, I can get for those values. And because n is down below here, as we go further in terms, they get divided by, like first one divided by 1, second divided by 2, third divided by 3, and so on and so forth. So you might not need that many terms. So say if you just wanted to have one term, so it's like it will go like this. So you have A0 over 2 plus I have n equals to 1. I'll go n equals to 1 also here. So n equals to 1 will be A over A0 is 2ab minus a over L. So let's write that down. 2ab minus a over L, and this will be plus a over pi, and I have a sine 2 pi b over L minus sine 2 pi a over L times cosine 2 pi x over L. And then you'll have from the Bm series, it's going to be minus a over pi And then you have a cosine 2 pi b over L minus sine 2 pi a over L, I mean cosine, both cosines, then sine 2 pi x over L. And you can see this is the m equals to 1 term in the cosine part, and this is m equals to 1 term in the sine part. And you can see you can combine these guys. These will combine with these guys, and these guys will combine with these guys. So you can further simplify. The second rule, you can see a over 2 pi, because you can see over here 2 pi, so it's going to be smaller than that. And then you have sine 2 pi times 2b, so 2 pi times 2b over L minus sine 2 pi times 2a over L times cosine 2 pi times 2x over L. And then you have a plus, then you have a minus 1 a over 2 pi now. And so you have a cosine 2 pi 2b over L minus sine 2 pi 2a over L. And then cosine 2 pi 2x, this is sine, not cosine. And so on and so forth. And you can again combine these guys and further simplify. So this is the Fourier series. Only when all the terms are contained, that's equal to that function. So I'm going to stop here. This is an example calculation for how Fourier series calculations go. You will need to practice the homework problems, make some plots to get a sense of how each series terms look like in different types of functions. So I'm going to stop here.